Japan's iconic Mount Fuji entered the spotlight once again after two moderate but widely felt earthquakes struck central and eastern Japan within the span of several hours. The stronger event, a magnitude 5.8 earthquake, occurred near Yokosuka in Chiba Prefecture at a depth of about 26.7 miles or 43 kilometers. Later the same day, a magnitude 5.7 earthquake struck near Oshino, a community situated close to the northern foot of Mount Fuji, at a depth of roughly 31.6 miles, or 50.9 kilometers. For many observers, the coincidence was immediately striking. One earthquake occurred within the broader region connected to the Fuji volcanic system, while the other took place to the east in the Kanto region. Did the two earthquakes have a common cause? Did the shaking near Oshino indicate changes beneath Mount Fuji? And why does this volcano continue to attract such intense attention whenever seismic activity occurs nearby? Those questions matter because Mount Fuji is not merely a national symbol. It is one of the world's best-known active volcanoes, rising to an elevation of 12,388 feet, or 3,776 meters, above central Honshu. The mountain stands near one of the most complex tectonic intersections on Earth, where multiple plates converge and interact. Earthquakes are therefore a routine feature of the region, even though most do not signal an imminent volcanic eruption. The first of the two earthquakes occurred on June 26, 2026, at 3:46 and 35 seconds Coordinated Universal Time. The epicenter was located about 1.9 miles, or 3 kilometers, southeast of Yokosuka in Chiba Prefecture. The earthquake reached magnitude 5.8 and originated at a depth of approximately 26.7 miles, or 43 kilometers. Several hours later, at 13:29 and 1 second Coordinated Universal Time, a second earthquake struck near Oshino in Yamanashi Prefecture, roughly 4.3 miles or 7 kilometers north of the town. This event reached magnitude 5.7 and occurred at a depth of about 31.6 miles or 50.9 kilometers. Both earthquakes were moderate in size by Japanese standards, yet large enough to be felt across broad areas. Japan experiences thousands of earthquakes every year because the country sits along the boundary zone of the Pacific Ring of Fire, where the Pacific Plate, the Philippine Sea Plate, the Eurasian Plate, and the North American Plate interact. Mount Fuji occupies a particularly important position within this tectonic mosaic. The volcano stands near the boundary where the Philippine Sea Plate descends beneath parts of central Japan. The subduction of oceanic crust generates intense heat and contributes to the formation of magma beneath the region. Over geological time, that process built the volcanic chain that includes Fuji and many other volcanoes across Japan. Yet Mount Fuji is not a simple volcano fed by a single shallow magma chamber. Geological studies indicate that it is a stratovolcano composed of multiple volcanic stages that accumulated over hundreds of thousands of years. The mountain visible today is the latest expression of a much longer volcanic history. The oldest known stage is often referred to as Komatake Volcano, remnants of which lie beneath the modern mountain. Later volcanic activity constructed Ko-Fuji, or Old Fuji, followed by Shin-Fuji, or New Fuji, which forms most of the present cone. Layers of lava flows, ash, scoria, and pyroclastic deposits record repeated eruptions through time. That long history explains why Fuji possesses its famous symmetrical profile. Successive eruptions built overlapping layers of volcanic material that gradually produced the towering cone recognized around the world. The mountain's near symmetry is remarkable, but geologically it remains an active volcano rather than an extinct landmark. Japan classifies Mount Fuji as an active volcano because it has erupted within the last several thousand years and retains the potential for future eruptions. The most recent significant eruption occurred during the Hoei eruption of 1707 to 1708. That eruption occupies a central place in Japanese volcanic history. Unlike many of Fuji's earlier eruptions, the Hoei event produced enormous quantities of ash and tephra that spread across wide areas, including what is now the Tokyo region. Contemporary accounts describe ash falling over large parts of central Japan. The eruption began on December 16, 1707, and continued into early 1708. One of its most distinctive features was the opening of a new vent on the southeastern flank of the volcano, now known as the Hoi crater. Geologists have long noted a striking detail about the timing of the eruption. Just 49 days earlier, Japan experienced the massive Hoi earthquake, estimated at approximately magnitude 8.6. The earthquake ruptured a large section of the Nankai Trough and generated destructive tsunamis. The close timing between the earthquake and the eruption has led researchers to examine whether the enormous tectonic event altered stresses within the crust beneath Mount Fuji. While the exact mechanism remains a subject of scientific study, the historical sequence is clear. A giant subduction zone earthquake struck southwestern Japan, and less than 2 months later Mount Fuji entered its last major eruptive phase. Importantly, that does not mean every earthquake near Fuji triggers an eruption. Japan has experienced countless earthquakes since the Hoi event, without a new major eruption of Mount Fuji. The relationship between tectonic earthquakes and volcanic systems is complex and cannot be reduced to a simple cause and effect rule. The two earthquakes recorded on June 26 occurred at depths of roughly 27 miles, or 43 kilometers, and 32 miles, or 51 kilometers. Those depths placed the events well within the crust and upper mantle region beneath central Japan, where tectonic processes associated with plate interaction commonly generate earthquakes. The Oshino earthquake is particularly notable because of its proximity to Mount Fuji. Oshino lies near the northern base of the volcano, an area that has experienced earthquake swarms at various times in the past. Seismic activity around Fuji is closely monitored because changes in earthquake patterns can provide information about stress within the crust and volcanic plumbing systems. However, a single magnitude 5.7 earthquake near Fuji does not automatically indicate magma is rising toward the surface. Many earthquakes in the region are tectonic rather than volcanic in origin. Determining the difference requires analysis of earthquake locations, depths, waveforms, deformation measurements, and gas observations. The broader Fuji region has experienced episodes of heightened seismicity before. For example, following the 2011 Tohoku earthquake and tsunami, researchers documented increased seismic activity around parts of central Japan, including areas near Mount Fuji. Despite concerns at the time, no major eruption followed. Understanding why requires a closer look at the volcano's geological setting. Mount Fuji sits near the junction of several tectonic domains in central Honshu. The Philippine Sea Plate is moving northwestward and descending beneath the Japanese archipelago. At the same time, stresses from the Pacific Plate and the complex collision zone of central Japan influence the regional crust. These interacting forces produce both volcanic activity and frequent earthquakes. In other words, Fuji exists in a landscape where seismicity is normal. The challenge for scientists is distinguishing ordinary tectonic earthquakes from signals that may indicate volcanic unrest. Modern monitoring of Mount Fuji is extensive. Networks of seismometers, global positioning system stations, tilt meters, and other instruments track changes in the volcano. Scientists watch for patterns such as persistent earthquake swarms directly beneath the volcano, ground inflation suggesting magma accumulation, and unusual gas emissions. As of the occurrence of these two earthquakes, the available information points to moderate seismic events in a tectonically active region, rather than a confirmed precursor to eruption. Nevertheless, any significant earthquake near an active volcano attracts attention, because stress changes can influence volcanic systems in ways that are not always immediately obvious. The magnitude 5.8 earthquake near Yokosuka adds another layer to the regional picture. Chiba Prefecture lies within the Kanto region east of Mount Fuji, an area affected by the complex interaction of the Philippine Sea Plate and the Pacific Plate beneath the Japanese mainland. Earthquakes of moderate size are relatively common there. Because both earthquakes occurred on the same day, some observers naturally wondered whether they were directly connected. Earthquakes can occur in clusters, and stress changes from one event can sometimes influence nearby faults. However, the two epicenters were separated by a considerable distance, and determining any causal relationship would require detailed seismological analysis. What is clear is that central and eastern Japan remain among the most seismically active regions on Earth. The same tectonic environment that built Mount Fuji continues to generate earthquakes across a broad area stretching from the Kanto Plain to the volcanic highlands of central Honshu. Mount Fuji's prominence often amplifies public concern. The volcano dominates the skyline across much of central Japan and carries immense cultural, historical, and economic significance. More than a scenic landmark, it is a living geological system shaped by ongoing plate tectonics. Its last major eruption, the Hoei eruption, demonstrated that Fuji can produce substantial ash falls affecting densely populated regions. Historical records show that ash accumulated in areas far from the volcano, disrupting agriculture and daily life. That legacy helps explain why Japanese authorities maintain detailed hazard maps and preparedness plans for future eruptions. Potential hazards from a future Fuji eruption would depend on the style of activity. Ashfall could affect transportation, infrastructure, water supplies, and aviation over a wide area. Lava flows would generally threaten regions closer to the volcano, while pyroclastic phenomena could pose more localized but severe dangers. Yet forecasting the exact timing of a future eruption remains impossible. Volcanic systems evolve over years, decades, and centuries, and periods of seismic activity do not necessarily culminate in eruption. Some volcanoes experience repeated unrest episodes that eventually subside without magma reaching the surface. For that reason, the most important context for the June 26 earthquakes is not that two moderate earthquakes occurred near an active volcano, but that they occurred within one of the world's most intensely monitored tectonic and volcanic regions. Japan's monitoring networks are designed precisely to detect changes that might indicate a transition from ordinary seismicity to volcanic unrest. Historical perspective is equally important. More than 3 centuries have passed since Mount Fuji's last significant eruption. During that interval, Japan has experienced numerous large earthquakes, including devastating events along the Nankai Trough and elsewhere, without a repeat of the Hoei eruption. At the same time, the volcano remains active in geological terms. Heat, magma, and tectonic stresses continue to exist beneath the region. The question has never been whether Mount Fuji is capable of erupting again. It is when and under what conditions that future activity might occur. The June 26th earthquakes therefore serve as a reminder of the dynamic forces shaping Japan. A magnitude 5.8 earthquake struck near Yokosuka in Chiba Prefecture at a depth of about 26.7 miles, or 43 kilometers. Later, a magnitude 5.7 earthquake occurred near Oshino, close to Mount Fuji's northern flank, at a depth of roughly 31.6 miles or 50.9 kilometers. Both events were significant enough to be widely noticed. Neither by itself establishes that Mount Fuji is preparing to erupt. Instead, they highlight the reality that Japan's most famous volcano sits within a constantly moving tectonic environment where earthquakes are an integral part of the landscape. Mount Fuji was built by repeated eruptions over hundreds of thousands of years as oceanic plates descended beneath Japan. Its modern cone represents the latest stage of a long volcanic evolution. The volcano's last major eruption occurred in 1707 to 1708, shortly after the enormous Hoei earthquake, producing widespread ashfall across central Japan. More than 300 years later, the mountain remains active, heavily monitored, and closely watched whenever seismic activity occurs nearby. The twin earthquakes of June 26 do not erase the distinction between tectonic earthquakes and volcanic unrest, but they do underscore why Mount Fuji continues to command attention. It stands at the crossroads of some of the most powerful geological processes on Earth. Although the June 26 earthquakes have drawn renewed attention to Mount Fuji, understanding their significance requires separating ordinary regional seismicity from the processes that accompany volcanic unrest. Japan's monitoring agencies have spent decades building one of the most comprehensive volcano observation networks in the world, precisely because earthquakes alone rarely provide the complete picture. A volcano is an interconnected system where magma movement, changes in underground pressure, ground deformation, gas emissions, and seismic activity must all be considered together before conclusions can be reached. Earthquakes associated with volcanoes generally fall into several categories. Some are purely tectonic, resulting from faults breaking under the continual stresses produced by moving tectonic plates. Others occur because magma forces its way through surrounding rock, creating fractures as it rises toward the surface. There are also long-period earthquakes, which often involve the movement of fluids beneath a volcano, rather than the sudden rupture of rock. Distinguishing between these different signals requires careful examination of their depth, frequency, waveform characteristics, and precise location beneath the volcano. The magnitude 5.7 earthquake near Oshino occurred approximately 31.6 miles, or 50.9 kilometers, below the surface. That depth is considerably deeper than the shallow volcanic earthquakes that frequently accompany magma movement immediately before many eruptions. Instead, it lies within a zone where tectonic stresses related to plate interactions commonly generate earthquakes. While every significant event near an active volcano deserves close attention, the available information alone does not indicate that magma is rapidly ascending beneath Mount Fuji. Mount Fuji itself is fed by a remarkably complex magmatic system. Geological and geophysical studies suggest that the volcano has multiple magma storage regions rather than a single enormous chamber. Magma generated by the melting of mantle rocks rises through the crust, where portions may accumulate at different depths before either cooling underground or eventually reaching the surface during an eruption. This intricate plumbing system explains why volcanic activity can vary dramatically from one eruption to another. Some of Fuji's prehistoric eruptions produced extensive lava flows that spread across surrounding valleys. Others generated explosive eruptions that blanketed large portions of central Japan with volcanic ash. The composition of the magma influences this behavior. Magma containing greater amounts of dissolved gases and possessing higher viscosity is more likely to produce explosive eruptions because pressure builds until it is released violently. Less viscous magma can flow more easily, creating lava flows that advance across the landscape rather than exploding with equal intensity. The mountain's nearly symmetrical appearance often creates the impression that it formed during a single eruptive episode. In reality, every visible slope represents countless layers deposited over hundreds of thousands of years. Lava hardened into solid rock. Explosive eruptions spread ash and cinders across the cone, and subsequent eruptions buried older deposits beneath newer ones. The result is one of the world's most recognizable stratovolcanoes, constructed gradually through repeated cycles of volcanic activity. The region surrounding Mount Fuji also reflects this long geological history. The volcano rises above an area containing numerous lava fields, volcanic plateaus, and lakes that owe their existence, at least in part, to ancient eruptions. Several lava flows blocked river valleys thousands of years ago, allowing water to accumulate and eventually form lakes around the northern base of the mountain. These landscapes preserve evidence of eruptions that occurred long before written records existed, allowing geologists to reconstruct Fuji's eruptive history through careful examination of volcanic deposits. Historical documents become increasingly valuable once written records begin to overlap with geological evidence. During the Hoi eruption of 1707 and 1708, observers documented heavy ash fall over communities located many miles from the volcano. Fields were covered with volcanic material, reducing agricultural productivity and affecting transportation. Although lava did not pour from the summit during that eruption, the enormous quantity of ash demonstrated that explosive eruptions can produce widespread impacts, extending well beyond the immediate vicinity of the volcano. The triggering sequence leading to the Hoi eruption continues to attract scientific interest. The massive Hoi earthquake that occurred 49 days earlier altered stress throughout large portions of central Japan. Researchers have proposed that these stress changes may have affected the magma system beneath Mount Fuji, potentially helping create conditions favorable for eruption. Even so, scientists emphasize that the earthquake did not simply switch the volcano on. Magma must already exist within the volcanic system, and numerous geological conditions must align before an eruption becomes possible. That distinction is important when evaluating present-day earthquakes. Moderate earthquakes occur regularly throughout Japan without producing volcanic eruptions. Likewise, some volcanoes experience prolonged earthquake swarms that eventually subside without any eruption at all. Volcanoes and earthquakes are linked through the same tectonic environment, but their relationship is neither simple nor predictable. Another reason Mount Fuji receives extraordinary attention is its location relative to Japan's densely populated corridor. Millions of people live within distances where significant ash fall from a future eruption could affect transportation, electrical systems, communications, and water supplies. Even a relatively modest eruption has the potential to disrupt airports, high-speed rail operations, highways, and economic activity across broad areas of central Honshu if prevailing winds carry volcanic ash toward major metropolitan regions.